Hello, my name is Amanda Hinchman-Dominguez. I'm an Android engineer at Groupon, and I'm also a Kotlin GDE. Today, we're going to talk about a brief history of memory leaks, why they're important, and how you can find them in your Android application. This talk is inspired from the work in progress O'Reilly publication, Programming Android in Kotlin, Achieving Structured Concurrency with Coroutines. In my research, I started seeing the strange relationship between coroutines and memory leaks with Android. Believe it or not, memory leaks have had significant impact on driving the evolution of Kotlin and Android. If you write Android in Kotlin, perhaps you've heard or have used coroutines yourself. If not, no worries. It's not necessary to be familiar with coroutines for this talk. Rather, I'd like for us to examine this timeline today. In 2017, when Kotlin coroutines came out officially at KotlinConf, the impression given was that the cost of spinning off coroutines is largely negligible. I believe the quote was that coroutines are like lightweight threads. However, a year later, Roman Elizarov comes back to KotlinConf with coroutines in practice, where he clarifies that coroutines are not like threads, but rather a way to structure your code. Hydra Conference, late 2019, Roman presents the idea of structured concurrency and actually clarifies that a job actually costs resources, particularly resource reference in a coroutine ends up causing a memory leak. So multiple coroutines can be run within a thread, and while it is not a thread, for controlled concurrency, this is a tale as old as time. A language releases new features into the wild, and sometime later, the makers realizes the impact of the potential performance hit for software development without the education of memory management. Why do memory leaks seem to play a large role in a lot of the talking points and examples shown in those talks? Well, I decided to dig a little bit more. So the internet started really talking about memory leaks back in 2016 when there was this release of the YouTube series Android Performance Patterns. Excellent series. I've seen it myself. I would highly recommend it if you're an Android developer. This is episode 3, season 5, called Memory and Threading. But the earliest evidence that I found was all the way back in 2009 in an obscure Android developer blog called Avoiding Memory Leaks. The guy who writes it even talks about some ways to avoid those memory leaks, and we cover some of that later in the talk. So as an Android community, we've known the existence of memory leaks for years, yet here we are, even in 2021, and memory leaks are scattered throughout some of the most popular Android applications in the Play Store. Why is this? There's a couple different reasons that I could put together. Early on, developers were educated via Android documentation to put memory leaks in their code base. Actually, I'm going to qualify that and clarify that. Android documentation has explicitly leak, but rather what happens is they tell you how to use a certain feature, and maybe they don't really pair that with how like the Android lifecycle might affect memory management, which kind of leads me to my next point. There's not a lot of education on how the JVM memory is affected by the Android lifecycle. Even for Kotlin, Roman says APIs to work with resources. It doesn't define any resources in its common library. So ultimately, responsibility of the Android developer to make sure that they understand how to manage their resources. If you're not familiar with memory leaks, don't feel discouraged. Memory leaks are, they're really hard. And as we can see in our timeline, we seem to be learning about new memory leaks all the time. In fact, internal memory leaks were popping up within Kotlin coroutines for at least 4 years. This is a reference to the Kotlin keeps KT1622. Coroutines does not clear internal state. Luckily, this was fixed in Kotlin 1.4. But for the first 2 years of this particular issue, many thought that this behavior regarding this memory leak was normal. So and people had noticed it for a few years, and then it took another few years to realize that this was something that had to be fixed. So why do memory leaks matter? Well, application quality depends on user experience. A slow application or one that takes up too much memory could mean the user uninstalling your application. Android has very limited resources and hardware capacity. Roughly 15% of Android users uses Lollipop and below on their devices. And of course, having memory leaks on your Android device can cause jank, lag, out-of-memory errors, and other strange behaviors. Okay, so what is a memory leak? Its simplest definition is when the heap holds on to allocated memory longer than necessary. There's also another way to get memory leaks, and that's when an object is allocated in memory but is unreachable for the running program. So, what does it mean for an object to be reachable or unreachable? How might garbage collection hold on to the reference or dispose of it? What is garbage collection? Well, to be able to answer these questions, we must go to the fundamentals of memory and threading in the Android and the JVM. The relationship between memory consumption and power consumption in Android is symbiotic. The more memory is freed from allocation, the more power it requires from the device. So when a device is low on memory, battery drainage can become a concern, or worse, bad user experience. The ability to kill and quickly resume applications in Android. So while it is true that you see less memory-related issues on newer devices, it's important to ensure that your app is still accessible to users with lower memory on their device. Hold on just a second. I just want to make sure, okay, I wanted to make sure that, you know, the connection's still good and all that. We're still good to go. Right, so it is your responsibility to do everything you can to manage processes to minimize power and memory consumption. It's very important. Okay, we're gonna talk about physical and virtual memory management. To make the most of limited memory on Android devices, as you know, iOS tends to have better RAM, and you know, that's one reason why Android phones tend to be cheaper. But I would say that in many ways, many Android software has superseded some of the capabilities from the other side. And we're going to talk about some of those mechanics. So to make the most of its limited memory, a device can use special hardware to enable virtual memory capability. So Android devices in particular, they use this thing called the memory management unit. The memory management unit is a piece of hardware that can map applications into physical spaces in memory, but uses a virtual address space to track where the application is occupying memory at runtime. Android virtual memory is based on a system called paging. And this is a system where RAM is divided into pages. In Android, these pages perform swaps between RAM and a page file. You can get 3 actual kinds of pages within this paging system. So it can be in 3 states. It can be used, cached, or freed. In addition, many of the RAM pages are allocated for framework and resources to be shared across all the app processes. The Android system sets a hardware limit of how much memory is allocated to virtual memory. So if an application is in need of more memory from the device can occupy free pages in memory. However, if the system needs to find more memory, it would take a look at the cached pages. But for the system to interact with the hardware is expensive because that requires hardware component interaction using the Android memory management unit, the MMU. So the more that the device interacts with memory, the more power drains from the and loading new memory in the free page can take additional time and resource consumption. So we talked about how virtual memory makes most of its limited physical memory in an Android device, but this paging system only describes the mechanisms of how applications are stored and loaded. So what about dynamic memory allocation for objects created at runtime? Well, at application initialization, a program in the Android OS called the Zygote. Just waiting for the passing motorcycle. 9 a.m., huh? Or it is, at least on this side. So at application initialization, a program in the Android OS called Zygote forks a new virtual machine instance at runtime. In turn, a store for dynamic memory allocation called the heap. So if when we're talking about the heap, I mentioned both Dalvik and ART, Android Runtime. Dalvik was kind of the old way of doing things, and ART is the current way that we do, that's what we currently have with Android. And we'll talk about some of those differences. Every single application has its own process in heap. Android sets a hard limit on the heap size for every app, which varies from device to device depending on how much RAM there is to work with. So if your app has reached heap capacity and tries to allocate for more memory, it will receive an out-of-memory error. Since the days of heap, several improvements have been made to better self-manage memory at runtime, and this is the Android runtime. To prevent problems like fragmentation, the Android runtime heap organizes objects by size and age into buckets. Most objects are allocated in the heap. Once they're allocated, they tend to quickly get allocated and deallocated just as quickly. For this reason, the Android runtime heap has a smaller subset bucket called the younger generation, which stores temporary objects. We have actually 3 kinds in the Android runtime. So if this bucket, the younger generation bucket, becomes full, then the heap will initiate a minor garbage collection where the memory management walks through a smaller subset of the heap instead of the entire thing like it used to in Dalvik. Objects in the older generation bucket contains objects that may have been alive for a longer period of time. Should this bucket fill up, a major garbage collection will occur. This causes a pause the world event, which will block threads in the process until GC is complete. In objects that stay alive long enough, they can get promoted to the permanent generation. Of course, the older and larger the object, the more intense the GC becomes when that heap is filled up. Garbage collection. Garbage is common in languages that uses a compiler. Garbage collection is a mechanism for reclaiming unused memory within a self-managed memory environment like the JVM that keeps track of memory allocation. So garbage collection in particular does 2 things. They find data objects in a program that cannot be reached in the future, and they reclaim resources used by those objects. Once it determines that a piece of memory is no longer being used in the program, it frees it back to the heap without intervention from the programmer. So garbage collection will look at certain things. They'll collect null object references, reassigned object references, or an object created within the scope of a method. And this is one of the huge perks with a self-managed memory environment. We don't need to worry about the overhead when objects are created or destroyed. However, this doesn't mean that it doesn't happen. Jank can occur if one is not careful with the kind of objects that a device holds in the heap. And on top of that, garbage collection executes on the main thread or the UI thread. So if you end up executing too many garbage collections consecutively, it can end up blocking your UI thread. This is really important to keep in mind. There is another exciting feature that the Android has, and that is thread local allocations. Android runtime's memory management and local allocations, which groups small allocations together by regions. Larger regions are paged aligned together, allowing other threads to run in the meantime. For every thread, a region is allocated and indicate the range, and these ranges can allocate on its own without pausing the world to do so. So no one region can access an object within a thread. The purpose of these regions is to create stop the world mechanisms as it's been in Dalvik, so that the regions themselves are locked for collection. Such features can help you greatly with safer concurrent practices. All right, so there was a whole lot of information that we went through, and I wanted to take a moment to kind of have some key takeaways with Rail both memory and threading, and also garbage collection and the self-managed memory environment. So some important key takeaways from what we just went over. An Android hardware component is used, there is battery drainage. And we're not just talking about interaction with memory, which is like excessive paging swaps, checks, clears, but we're talking about other hardware components that are used in Android. So we could be talking about being able to use the camera, using your location, your GPS on the device. Anytime you have like heavy graphic jobs, maps, and then even network calls, will turn on the Wi-Fi radio, and they'll even stay like just like wait and calls coming in. Garbage collection will help manage your heat, but calls to garbage collection can end up blocking your UI, and if you're not careful, it can kind of like have this vicious cycle where it keeps trying to trigger over and over again. So you want to be very frugal with your memory allocation. Consumption. Add memory exceptions in the. All right, so there's a lot going on with memory management as it is, but managing memory becomes significantly more complicated when threading is introduced to the equation. Before we can understand how threading complicates memory management, we must take the time to understand the Android threading system. Android is an event driven frameworks. An Android application has a main UI thread and a set of allocated threads. So the main thread will process events, but the work that is longer running should always be sent to the background thread. Other operations will also execute on the main events, system events, user and service callbacks, and device alarms, so on and so forth. Some characteristics of the Android threading system might actually surprise you. Consider the following scenario where the user clicks on a button in the application. Surprisingly, when a service starts running, the thread system does not necessarily create a separate thread just to have that service running on it. All the Android components, when they start, they do start by default. Therefore, it is your responsibility to offload longer running work to the background thread and return the results back to the UI thread so as to prevent blocking the UI thread from being able to detect other events like network calls, user interaction. So the Android UI toolkit has a very special threading system to handle Android components like views and view groups, which can only interact and manipulate widgets and views on the main thread. UI views on the thread is not thread safe. Android components must be confined within the UI thread at all costs. So if you try them on other threads, this can cause runtime errors and other weirdness. So when a user is on an application and rotates the device, the activity is destroyed. Not only must we be concerned about what data we wish to preserve in the view state, but we also must be vigilant for potential memory leaks. If the activity, the rotation destroyed spawns a whole bunch of worker threads, then those threads will contain unreachable references to the activity. So even though the activity instance is held in the worker thread and it's technically been destroyed, it's not able to be garbage collected. All right, so some key takeaways. Every Android component has a life cycle of its own: activity, service, broadcast intents, and so on. Every thread has a life cycle of its own. Killing an activity or even the UI thread doesn't necessarily kill a background thread. Make sure you don't block the UI thread, and you should always force top-level activity fragment to be the sole system responsible for updating UI objects. So ultimately, just make sure you're following the constraints of the UI component system. I think that's just an important thing to keep too. So let's look at this scenario one more time. This was the scenario where we have a UI thread and we spawn off another background thread with an activity referenced in that worker thread. This is actually a memory leak. Remember, It's possible for a memory leak to occur when the heap holds on to allocated memory longer than necessary. We have the heap holding a reference to activity A. Whoops. Because the background thread has a life cycle of its own from the life cycle of the activity, it's possible to not dispose of activity A in the scenario where GC should be called. So if we spawn off a worker thread, we have activity A, and we end up rotating the device, that instance gets killed in the UI thread, but you're still holding a reference in the worker thread. This is a memory leak, and this is something you should definitely avoid doing. And when an object is allocated in memory but becomes unreachable for the running program, it's possible for the reference to activity A to become unreachable. Should we wish to replace the background that is still trying to perform heavy work? That's a yikes. So we have, when we're talking about memory leaks, we actually have two kinds of memory leaks. We have explicit memory leaks and implicit memory leaks. Explicit, we inject an Android activity, context, view, or other Android UI toolkit component into another thread. And you can also do it by referencing a view or activity as a static reference, which means that it's never going to get garbage collected. This is something you want to avoid doing. I do want to the code below. There's this kind of like little function called paginate. Maybe it's like to paginate like cards or something like that. Doesn't really matter. But you'll see that we're feeding in the context and the view pager. The view pager is part of the Android UI toolkit. And we have this handler which kind of creates a new thread. So we're starting a background thread, but then you'll see in the go-to page, we're making a reference to the Android UI toolkit. This is a memory leak. This is something you do not want to do. You just want to make sure that anytime you're making references, like I said, to the context, the view, activities, fragments, etc., you want to make sure that this is occurring in the main thread. This is an explicit memory leak because this is something that you can see reading the code. So it's also possible to cause accidental leaks, meaning that other code behind the scenes, when we're talking third-party libraries and even Android code itself, the Android API code. So until async task had been deprecated in late 2019, it was the most commonly used Android primitive to send a task to the background thread. So despite its good intentions to enable easy multi-threading in Android, its most common uses were for integrating results back into the UI, which often ended up causing memory leaks, miscalls, unpredictable behaviors. And what's also kind of funny is that the same year that Roman Elizarov is kind of like talking leaks can occur with threading and coroutines, and there could be serious memory consumption, is also kind of the same year that Android ends up deprecating async task. I thought it was just kind of a fun correlation. I don't know, I can't say if it was a cause and correlation, but I'm sure there are a lot of correlations going around at the same time. Ooh. All right. Okay, so this is actually a reference to the async task. We have more specific memory leaks. What you want to watch out for is using an inner class of async task, especially within an activity or a fragment. It's going to hold an implicit reference to the enclosing class until the object is destroyed. So if you look at this code, if the main activity is destroyed, an implicit reference could be held to some async task should the thread still be actively running, meaning that the heap is going to hold a reference to the main activity even if it's already dead, which could lead to memory leak. Is there any way to fix this? Well, many tutorials over the years have offered the option of using a weak reference to hold an Android UI toolkit component like context or view. This is something that I've seen commonly, like even in like work code bases in various places as well. theoretically, when the weak deallocated, the reference to the fragment should also be deallocated, preventing the possibility that the reference is held longer than necessary. But the catch is in the unspoken precondition. Remember, weak reference is not lifecycle aware for UI components like activity, fragment, context, or view. So when you finally get a reference of the fragment, you would have to make additional checks on the state of the fragment. This is a potential code smell for its potential of memory leaks. Can you do it this way? Yes, this is not necessarily a wrong approach. Trying to work with Android component can be really tricky. Like null safety, depending on every developer to deallocate objects in memory according to the lifecycle of an Android component, that really could be avoided altogether. Then sharing, notifying changes from one thread to another. So one way could be that you use an RX bus event and async task so that whenever it is destroyed, the views would have to unsubscribe from the event bus. Or my most recommended way is using the Android view models and live data. And one of the wonderful things is that it's all activity and fragment life cycles, and it can clean its own references up. So permanent memory leaks are obviously really bad. Luckily, those memory leaks are easy to catch reviewing your code, and that's what makes those memory leaks explicit. But implicit memory leaks, they can be and not immediately detectable. So this, I meant, you want to be wary of reference use of Android resources. But there's this other, it was a bit of a contentious item, I think, like a few years ago. And basically, it wasn't even written in Android documentation initially. Android developers were expected to know this, and I'm like really surprised this is something that's like not widely known. But not clearing view references in a fragments on destroy view causes these views to be retained using the backstack. So maybe this is like not a big deal for smaller applications, but if you're working on larger applications, this can become a serious issue. So the reference to this particular issue comes from the guy who made Leak Canary. There was an issue tracker a little while back where someone had submitted the possibility of Android or memory leaks with this particular issue. And surprisingly, like the way it was resolved was that they're saying that this is actually intended behavior, and that Leak Canary takes kind of like a conservative approach, and they ask you to null out the references to the views on destroy view. And they write in here, while this is not technically a leak, as it will get cleaned up eventually. I said the simplest definition of a memory leak is anytime that memory is being held longer than necessary. So what that means is that you're holding references to the fragment until eventually we trigger garbage collection. This is a memory leak, and he's absolutely right. So just remember, if you're using view references in your fragment, make sure that you're nulling it out. You're clearing out the listeners as well. Practice. So would totally recommend looking into that. Excellent. So I do have a real example of using Leak Canary. You know, this is not the only way you could profile your app. There's actually a couple different ways you can profile your app. I have two that you can see right here. We have Android Studio running, and in particular, the bottom half is Android. And if you haven't profiled, I recommend doing it. We're actually looking at what it looks like the CPU profiler on top of Leak Canary. If you're not able to see the quality of the text, I will definitely read it out. Excellent. So the quality is okay. You'll see here that actually, I'm going to pause this just a second. So this particular application is graphical maps for offline. And that's why it takes ages for something to appear. So we go to creating a new map. So you program, and then we're waiting long enough to see the tiles start to appear. So remember, the network's kind of slow, so we're just kind of waiting. Here we're running the profiler in the backgrounds, the memory profiler in particular. So we've rendered it, and then I started twice. And I start doing it a couple more times. So at this point, I'm going to have you turn your attention to the code behind it. I had commented out .destroy, which is kind of like a maps, and then I also chose to not to comment out the nullifying reference to the view. So this should be an expected memory leak. So map view has internal threading, and they use like this tile provider to fetch the tiles. When we rotate the device, on destroy view is invoked. So like I said, we intentionally commented out the map view destroy and nullifying the threads, which would cause the background threads to stop. So without that, the background threads are still running. And you'll see here that memory leak had actually, Leak Canary had actually detected some memory leaks coming from this like thread that we have running in the backgrounds. So unfortunately, reference on the map view itself, and the map view ends up leaking. Map view, as any other view, they have, and the reason why this is a memory leak is because the map view, like any view, all views are going to have an implicit reference to the parent context. And that's why Leak Canary detects this memory leak. So the faulty design is that we didn't stop the ongoing work. Obviously, you want to make sure that you add your destroy for the map view, nullify those references in the fragment. So this is kind of a cool thing. If you haven't tried Leak Canary or like profiling your app with Android Studio, would totally recommend doing it. But I do have some wise words. Maybe that if you were to try out Leak Canary, make sure that you and your team are ready for that conversation, because sometimes the more you dig, or the more you find, the more you want to dig. I'll talk about that a little bit more at the end if people have questions about that. Sometimes you can start digging for memory leaks in your profiling app, and what I would say is you want to get the lowest hanging fruit. Like some memory leaks that I found in applications I work on, like they're kind of like at the spine of the application. It's too dangerous to take it out, stuff like that. Like with memory leaks, you definitely want to start with low hanging fruit. If it's like the smallest amount of work and doesn't interrupt anything, like those are big wins. Yeah. Well, continuing on. Here we go. So we have some lessons that I kind of like summarized here with avoiding potential memory leaks. Make sure you profile your code and how you interact with the Android API framework. Make sure if you follow the constraints of the Android threading model. Make sure that you profile your app at some point with Android Studio or Leak Canary, and ask yourself, should I be interacting with hardware components? And over here, I think I have it looks like part of the Android stack with like cameras, contacts, or some applications. There's also different kinds of frameworks that you're working with. Oh, okay. Also, pay special care to static references since they're stored longest in the heap. Never store Android components like activities, services, views, context as a static reference. Like, do not do that, because otherwise it's never going to be garbage collected. Do not reference activities, views, fragments, context, and other Android components outside the UI thread. Make sure it's in the main thread. And use Glide if you can if you're like loading images. But if you have to work with bitmaps, make sure you're recycling and nullifying those bitmaps. And also avoid the use of persistent services whenever possible. There are a lot of great tools that you can use now, like Work Manager, Job Scheduler. I would avoid using a service unless you absolutely have to. And if you have to use a service, make sure that you're not accidentally creating a bounded service or something like that, unless you absolutely need it. Because, for example, bounded services, they will stay alive for as long as the life cycle items that they're bounded to. So it makes it kind of difficult to keep track of those things. And then, if it's the great thing is you can use Android Studio's profiling to determine which services you're running at a certain time. There's some really great tools for that. So yeah, just if you're working with services, be extra careful and make sure that your service is not running forever. Okay. I hope all of you have enjoyed what I've had to share so far. I know that there's like a lot of issues with like memory leaks in Android, and even like native languages, they don't offer a lot of tooling on that. And until we like figure out some add-on libraries for Android that makes resource management easier, we have to start educating people on how it works and how to manage resources properly. And so that's what my colleague, Pierre Lawrence, and myself were trying to take on. Much of the contents of this presentation comes from a book that we've been co-writing together, and that's the Programming Android with Kotlin book. And a lot of these images and content does come from this book. It's kind of like touching upon a few different chapters. Just like I said, this talk is inspired from that book. Like this was just something I thought was like a really cool thing to look into timeline-wise. And we do have early release open. I think it's chapters. And I think you get like a week free trial or something if you wanted to check out the current rough draft, if you want to see it. Hoping that it comes out in 2021. You can also follow me on Twitter. Yeah, so thank you so much.